In this presentation, we will focus on the Meteorological Data Acquisition System, MDAS, or your weather station for your PV systems. From our previous discussion on the areas of the PV power plant, here is where the MET station is located, which is part of the array, and usually located within a skid or a pad that are close to the modules. Meteorological data acquisition is a part of your SCADA system that records and collects the power plant's weather data. The key to reliable performance monitoring and fault detection methodology is to have a good and simultaneous ground measurements. This can be achieved by incorporating a weather station on site to measure plane of array irradiance, module and ambient temperature, global horizontal irradiance, humidity, and wind speed. Over a period of time, MET station data can be used to predict weather patterns, allowing more accurate forecasting of the future energy yield. Components of a meteorological data acquisition system. Our first focus is going to be on those irradiance sensors. Let's step back a bit and discuss briefly the concept of irradiance and insolation, which are common terminologies being used in the solar industry, especially when it comes to your PV system performance calculations. Irradiance is the instantaneous measurement of the amount of sunlight you're getting on a specific area. This is equivalent to power. The unit of measure is in watts per meter squared. Irradiance determines or is linear to the power being generated by your PV system. Insolation, on the other hand, is the integrated irradiance. This is equivalent to energy. It is the measure of how much sunlight fell on a specific area over a specific period. For more information on the difference between power and energy, you can check out the link to a separate video on the upper right-hand side corner of this presentation. Pyranometers. The primary PV irradiance detector is the pyranometer. It's usually a horizontally mounted sensor that is used to measure GHI, or global horizontal irradiation. GHI is mainly the total solar energy received on a unit area of a horizontal surface. Here is a graphical representation of GHI, which includes all three parameters: the direct beam component received on a unit area of a surface, or what we call direct normal irradiation, or DNI, the diffused horizontal irradiation, DHI, and dose reflected radiation. The total energy received by the pyranometer will be our GHI. The way the pyranometer captures irradiation is through the thermophile, and the resulting increase of temperature is being measured via thermocouples connected in series or series parallel to make a thermopile. The differential voltage output of 0 to 20 millivolts is in relation to the amount of incoming radiation. These instruments are classified and calibrated to ISO standards, and the pyranometer's calibration factor is very stable over time. PV modules and reference cells, on the other hand, are specified under Standard Test Conditions, or STC. These are conditions of 25 degrees centigrade ambient temperature, 1000 watts per meter squared global solar irradiance, air mass of 1.5, and no wind. These conditions are far from realistic values in the real world, while the pyranometer shows the real-world performance with a more accurate measurement. Another advantage is that when PV cell types are different within a single power plant, a separate reference cell for each type should be used, but only one pyranometer is required for monitoring all types. However, pyranometers cost more than silicon-based cells, and when used on a tilted surface, its calibration may vary. Reference cells, on the other hand, are silicon sensors that are cheaper than thermopile pyranometers and mounted within the same tilt or angle with that of the modules. By using the same make and model with that of the PV modules in the field, this enables precise measurement of PV performance to detect degradation or deviation from expected performance. For silicon sensors, the current of the reference cell is measured by measuring the voltage across a small resistor that is included in the reference cell package. The current delivered is proportional to the irradiance. Typically, these are cheaper than pyranometers and consist of a PV cell, often using crystalline silicon. Temperature compensation can be used to increase its accuracy, but its scope is limited by the spectral sensitivity of the PV cell compared to thermal pyranometers. Here is a tabular comparison between the silicon-based reference cell on the left and thermopile pyranometers with respect to each category when it comes to implementation, as well as aspects of PV systems performance monitoring. Studies have shown that silicon cells working in high air temperature and high humidity conditions causes a significant reduction in cell efficiency. High relative humidity also has negative effects on solar radiation and reduces cell performance. Humidity refers to the amount of water vapor in the air or in the atmosphere. It is characterized not by moist in the air, but by the water content of the mixture of water vapor and other components of the air. Humidity can slow efficiency in two ways. First is with those tiny water droplets, like beads of sweat, and reflect or refract sunlight away from solar cells. This reduces the amount of sunlight hitting them and producing electricity. Second, consistent hot or humid weather can degrade the solar panels themselves. Relative humidity is the percentage or ratio of the amount of water vapor in a volume of air at a given temperature, and the amount that it can hold at a given temperature. Nowadays, temperature and humidity probes uses advanced capacitive sensor technology. How it works is that the dielectric in the sensor absorbs water vapor proportionately to the ambient humidity. A change in relative humidity changes the capacitance of the sensor, which is proportional to the relative humidity in the air. The sensor is then placed inside a solar radiation shield that protects the sensor from driving rain, snow, and insect intrusion to maintain reliable measurements. The sensor itself should have a reliable and a fast response rate. Also, a wide range of data logger compatibility as well as operating temperature. Once again, the effect of temperature on solar cell performance is this. Cooler panels allow more energy to get through, like an electric current, than hot panels do. Solar panels cooled by 1 degree Celsius are 0.05% more efficient. This percentage adds up over time. Back of module temperature sensors, or RTDs, surface sensors that are placed with direct contact on the back of one of the modules in the array. Module temperature uses RTD, or resistance temperature detection, which means any change in temperature results in the change in the resistance of the RTD element. These elements are usually made of platinum. These are usually specified as PT1000 or PT100. The 100 in the PT100 series denotes 100 ohms resistance at 0 degrees Celsius and 1000 ohms resistance at 0 degrees Celsius for those PT1000 series. These sensors are mounted at the back of one of the modules in the array with a self-adhesive tape, clips, or as needed, a thin layer of adhesive is being applied to the side of the sensor that is intended to make contact with the module surface. As a PV panel's efficiency is affected by temperature, measuring and understanding this information helps form a greater understanding of your panel's performance. Here is where the wind comes in. The wind cools solar panels. Though it won't make or break your solar panel's production overall, but it does make a difference. Generally, it has been observed that module temperature can be reduced by 50% when wind speed is increased to more than 10 meters per second and wind speed sensors are there to measure it. The most common anemometers are those mechanical ones, which are cup and star. The way it works is that the wind generated by the airflow drives the top three wind cups to rotate, and the central axis drives the internal sensing element to generate an output signal, which can be used to calculate the wind speed. These mechanical types have low threshold and responds accordingly to subtle change in wind speed. Ultrasonic anemometers uses ultrasound to determine the horizontal wind speed and direction. The measurement is based on transit time, the time it takes for the ultrasound to travel from one transducer to another, depending on the wind speed. The transit time is measured in both directions for a pair of transducer heads. Using two measurements for each of the three ultrasonic paths at 60 degrees angle to each other, this is how the ultrasonic anemometer computes the wind speed as well as the wind direction. Since this ultrasonic anemometer has no moving parts, they are virtually maintenance-free. The performance of the sensors does not degrade with wear and tear, nor is affected by natural contaminants such as salt, dust, or sand. But you may want to proceed with caution when handling and during installation, as hard impacts on the wind sensor may damage the device. Another component in our MDAS is the barometric pressure sensor to measure changes in the atmospheric pressure, and are typically located within the data logger enclosure. Barometric pressure transducer uses a variable capacitance sensor that is made using ceramic material fused together with glass and usually gold to make up the pressure element. Once it senses absolute pressure, it will convert this pressure to a proportional high-level analog output. Now we move to the data logger, which is the data concentrator for the MDAS. Data loggers are electronic devices which automatically monitor and records environmental parameters over time, allowing conditions to be measured, documented, analyzed, and validated. The data logger contains a sensor to receive the information and a computer chip or a memory card to store it. The example data logger being shown here is the CR1000 from Campbell Scientific, which on board has a basic-like programming language that supports data processing and analysis routines. It is called CR Basic. For those Campbell Scientific data loggers, we're going to be using this CR Basic editor to set up our data logger for it to know how to interact with the devices. On this example program, we have this first section. These are lines or comments denoted by an apostrophe, are commented out and has no significant relationship to our program. These are mostly intended for internal notes, such as revision versions. Starting at line 19, we have a public and variables declaration. If you need a variable to be monitored in real time, you can set it as public. Starting from line 26, we will declare more variables for each of the inputs we have on the wiring panel. Starting at line 101 is our constants declaration table, as we need to declare calibration constants for each of our sensors respectively. After that, we will move to the data tables at line 135. These are the tables that we want to see, as well as those we will send to the SCADA server. If you need to get more information on the syntax, all you have to do is right-click on the function. For the data collection, please take note that it will be determined within each of the data table we have declared. In this example, we have set it to collect and generate a data table every 15 minutes. That's going to be your data resolution right there. From line 138 to 149, we will define the calculations we need. It can either be an average, maximum, sample, or totalized. Right here on line 153, we have some subroutines that's related to a reference cell calculation. From line 163, our program begins. Here we're assigning serial numbers. Those are our static values for each of our sensor, as well as network details. Starting at line 198, the data logger will then scan through each of the variables that we have above with an interval of 2 seconds. And that completes our program. Here we have a simple representation of how the data logger works. We have our instruments on the left that are connected to our data logger, either through serial or Ethernet based on the OEM specifications and depending on the network protocol, PAC bus, Modbus, SDI12, and the like. From the data logger program we did earlier, we set it up to collect every 15 minutes with the current timestamp of 11:45 in the morning. Looking at the clock now, it's 12 noon, and the data logger again will pull the data from each sensor on a 2-second interval, then arrange it based on the table definition on the program. This will then be stored within the data logger. Those data tables can then be pulled remotely over the internet or collected by your SCADA server. Given the predefined 15-minute interval, the data pull process will continue until the next scheduled data collection. Same procedure, again at 12:15, and will continue moving forward. Again, the data collection can either be 1 minute, 5 minutes, depending on the interval collection that was indicated on the preloaded program. The use case that we have here is on a 15-minute data resolution or data collection interval. For the data logger mentioned previously, and the need for an uninterrupted data collection, it should have a dedicated power supply. Here we have the PS100 and PS200. To protect our equipments from wear and tear due to dust, moisture, high temperature, as well as pests and other animals, we would need a met station enclosure that has an IP55 or IP66 protection class rating. Some other optional components would include rain gauge, sensors for soiling and snow, as well as a lightning rod to protect the MDAS from the harmful electrical discharge of a lightning strike. MDAS location. Location of the MDAS significantly affects the data gathering and data quality from it. MDAS that are installed in poor locations gives incorrect data about the various parameters, thus eliminating the entire purpose of installing a weather station. While selecting the location of installation of the MDAS, here are the factors that need to be considered. There should be no high-rise buildings or trees near the MDAS tower. The pyranometers should be free from any shadows throughout the day. The tower itself or the met mask does not cast any shadow over the pyranometer or the PV modules. The wind speed and wind direction sensors should not have any structure nearby that can obstruct the wind flow. The top of the rain gauge should be free from any shade or obstacle. The module temperature sensor should be fixed at the back of the PV module. And lastly, the cable lengths required for sensors should be minimized. For a large-scale power plant, MDAS must be within 100 meter of the SCADA communication panel and 70 meters away from the reference cell's junction box or J box. Basic practices. Let's start with calibration and maintenance. Each sensor type is subject to aging, and accuracy reduces with time. Therefore, it is important to recalibrate at least every 2 years. It can be expected that annual GHI solar irradiation from well-maintained ground-based sensors can be measured with a relative accuracy of ±3% to ±5%, depending on the category of the sensor, position of the site, calibration, and maintenance. Periodic pyranometer calibrations are essential. Keep it clean. Use good wire management practices and label those signal lines. Care must be taken to avoid shade or wind obstructions for the tower as well as the solar array. Make sure all measurement equipment are grounded. Reliable hardware is worth the cost. If the data is to be used for modeling or analysis, then it has to be as accurate and complete as possible. Unreliable hardware can impact results because of missing, inaccurate, or noisy measurements. Significant recommendations are also listed in this table for a more sustainable weather station as well as good data quality. O&M strategies related to your MDAS data acquisition. The number of met station required is mostly dependent on the site's capacity. The typical requirement is 2 met stations for a PV power plant up to 20 megawatts, and 1 additional met station for every 40 megawatts after that. Even small-scale DAS projects usually prefer 2 met stations. In any given scenario that you believe that the data you're getting is unreliable or far off from the predicted weather data, it's always a good strategy to use a nearby weather station as backup or for comparison. But take in consideration the distance between the 2 sites. It should be within a 5-mile radius. Another good strategy or a replacement for ground measurement data, occasionally or permanently, is the use of satellite-derived data. One advantage of a satellite resource assessment is that data are not susceptible to maintenance and calibration discontinuities. Satellite-derived data offers a good wide geographical coverage and can be obtained retrospectively for historical periods during which no ground-based measurements were taken. This is especially useful for assessing hourly or sub-hourly time series or aggregated long-term averages. For locations that have a low density of meteorological stations and rely on satellite data, site solar resource monitoring may be considered during the feasibility stage of the project. In general, the measurement data for a minimum of 9 months can be used to reduce existing bias and improve the estimation of the long-term mean. The best results, however, are obtained by monitoring for a minimum of 12 months to better capture seasonal variations. Here is a list of reliable satellite data providers that you could choose from. However, There are some things that you may need to consider when choosing to move or use satellite data instead of the MDAS or actual ground measurements. First off, your desired data granularity may not be available in some websites. Different satellites means different time or space resolution and is fully dependent on the data provider. The more variable the climate, the less the accuracy. And tropical climates are the most complicated.